Now let's tackle something more challenging. Prove that limit of x squared as x goes to 2 equals to 4. Again, step 1. Find delta. Given epsilon greater than 0, we need absolute value of x squared minus 4 be less than epsilon when absolute value of x minus 2 is greater than 0 and less than delta. So keep in mind that this is my f of x and this is my L. Here, this is my x minus a. Okay, so a is 2, that's minus 2. F of x is x squared, L is 4. So that's why we put it this way. All right, so first let's factor. Remember, when we are on the stage of finding delta, we are starting with the then statement, or in this case, the conclusion, right? So let's factor it out. We have x minus 2, x plus 2, less than epsilon. Okay, now here where it gets tricky, we need to control x plus 2, and if we assume delta to be less than or equal to 1, then this guy will be less than 1. So let me write that. Assume delta is less than or equal to 1, then x minus 2 is less than 1, which implies that x minus 2 is less than 1 and greater than negative 1. So if we add 2 to all three sides, we get x is less than 3 and greater than 1. So from here, we want to, again, control x plus 2, so we will add 2 to this expression, to this inequality, so that we reach this x plus 2 to find the upper bounds. So we need to add 2 again. So we have x plus 2, which is exactly this guy right here, right? That's going to be greater than 3 and less than 5. Therefore, we can say that x plus 2, the absolute value of that, is less than 5 when x minus 2 is less than 1. So x squared minus 4 equals to x minus 2, x plus 2, less than 5 times x minus 2, right? So to make this less than epsilon, we need 5 times absolute value of x minus 2 to be less than epsilon. And if we divide everything by 5, we get x minus 2 less than epsilon over 2. So this is what we will choose our delta also to be, right? So therefore, delta, or choose delta to be minimum between 1 and this epsilon over 5. And it turns out that this epsilon over 5 is always smaller, so this is what we will use for the proof. But you need to include this 1 because this is what we assumed in the first place when we were trying to find the boundary on the x plus 2, right? So for this one, since you see that this is the same as the expression in the if statement, we can find the relation between delta and epsilon, and we found that it's going to be epsilon over, oh my goodness, it's over 5. Okay, it's going to be epsilon over 5. But for this one, we don't have any bound right now, so we need to kind of artificially create that bound by assuming that delta is less than or equal to 1. So we would find that the upper bound for x plus 2 is 5, right? So this is how we will write or choose, find our delta. And for quadratic functions, this is usually the case. You need to find the minimum between some two values. Now, going to the second step to write the proof. So let epsilon greater than 0 be given. Then choose delta to be minimum of 1 and epsilon over 5. Assume x minus 2 is less than delta. And since delta is less than or equal to 1, we have x minus 2 absolute value is less than 1, which implies that absolute value of x plus 2 is less than 5. So we will start with this if statement to get to the then statement, which is supposed to be x squared minus 4 less than epsilon. So this is our end goal, right? We start from here and we work it through to get to the end goal. So let's start with, we start from here. So let's start with our x minus 2 less than delta. So we will multiply all three sides by 5. We get 0 times 5 is 0. So we have 5 times x minus 2 less than 5 delta. And now we said that 5 is the upper bound for x plus 2. So we can simply just substitute it. We have absolute value of x plus 2 times x minus 2 absolute value less than 5 delta. Now we can put them under one absolute value and we have x plus 2 and x minus 2 less than. Now we also chose our delta to be minimum between 1 and epsilon over 5. So I will substitute this delta with epsilon over 5 and I get 5 times epsilon over 5. And as you can see, I can cancel these 5s. And also I can apply the difference of squares here and I get this expression x squared minus 4 on the left side, and it's less than, since we cancel these 5s, we have only epsilon left. So we proved this inequality, or we also can say, therefore, limit of x squared as x goes to 2 equals to 4. And you can also say by definition, by the precise definition, or using the epsilon delta proof. Now let's look at another example. We have limit as x approaches 2 of x squared plus 2x minus 7 equals to 1. So first step, guess a value of delta. So delta should be greater than 0 and epsilon should be greater than 0. So if x minus 2 is greater than 0 but smaller than delta, then x squared plus 2x minus 7 minus 1 absolute value is less than epsilon. So we will start working with the then statement to find the bounds or for our the potential values for our delta. So we would have here x squared plus 2x minus 7 minus 1. That's gonna be negative 8. And that is, if we factor it out, it's gonna be x plus 4 and x minus 2 less than epsilon. And we can write it as x plus 4, just separate them into two absolute values. Now, look at this. In the if statement, we have x minus 2. So this x minus 2 can be bounded by the relation between delta and epsilon. But this x plus 4 needs to be controlled, right? So we need to find the upper bound for this expression to use the proof. Okay, so from here, what we need to do is let me write it. We want to make x minus 2 small enough so that x plus 4 times x minus 2 is less than absolute. So we let delta to be less than or equal to 1. That would be our initial guess. From here on, we say x minus 2 is less than 1. From here, we have x minus 2 less than 1 and greater than -1 as before. We add 2 to all sides. We have x is between 3 and +1. So from here, what we need to do is we need to add 4 so that we can find the upper limit or upper bound for this x plus 4 expression. So we'll just add 4. And we have x plus 4 is less than 3 plus 4 is 7 and greater than 1 plus 4 is 5. So we will use this upper bound here because this is a bigger value. So therefore, x plus 4 is absolute value of x plus 4 is less than 7. This is the upper bound we will be using to guess our delta. So in going back, we have x plus 4, x minus 2 less than delta. Again, we said that the upper bound for x plus 4 is 7, so I'll just substitute it here. I have 7 times the absolute value of x minus 2 less than epsilon. Now I can simply divide everything by 7 and I get x minus 2 absolute value less than epsilon over 7. So I choose my delta to be minimum between 1 and epsilon over 7. Now, second step is the proof. So we start with if x minus 2 is less than 0, sorry, is greater than 0 and less than delta, we have x minus 2 less than epsilon over 7 and x plus 4 less than 7. Okay, so x minus 2 is less than delta. This is where we start. Now we start building up on that. We will multiply both sides by 7. We have 7 minus 2 less than 7 times delta. So as you can see, we're kind of undoing the step that we did before to rigorously show the proof of this limit, definition of this limit. So now we will have x plus 4 times x minus 2 because 7 is the upper bound for x plus 4, right? And here we have 7 times. Now I want to substitute my delta with epsilon over 7, right? Because that's what I chose it to be. So I will have 7 times epsilon over 7 where I can cancel those. Now this expression on the left side I can put under one absolute value and I have x plus 4 times x minus 2 less than epsilon. And here I will FOIL those and I have x squared plus 2x minus 8 less than epsilon. Now we're not quite there yet, right? Because we want to have f of x minus L less than epsilon. But for that to be true, we need to write this expression as x squared plus 2x minus 7. But what we can do is break down this -8 into -7 plus 1, right? So I will write x squared plus 2x minus 7 plus 1. Oh, sorry, minus 1 less than epsilon. And as you can see, this is my f of x, this is my limit. So therefore, limit as x approaches 2 of x squared plus 2x minus 7 is equal to 1 by the definition of a limit. Okay, now let's look at another example that will require us to use another formula. So limit as x approaches 2 of x cubed equals to 8. All right, so we need to prove that this is true. Now, first step, again, we need to guess the value of delta, right? So we start with if x minus 2, the absolute value of x minus 2 is less than delta but greater than 0, then absolute value of x cubed minus 8 is less than epsilon. Now look at this expression x cubed minus 8. Remember that we have a formula a cubed minus b cubed, which is a minus b, and a squared plus ab plus b squared. So we will apply this formula here to break it down into x minus 2, x squared plus 2x plus 4 less than epsilon. So now let me break that down into two absolute values. I have x minus 2, and another one is x squared plus 2x plus 4 less than epsilon. Okay, so now notice that this x minus 2 in the if statement is the same as in the then statement. So this would be controlled by delta being written in terms of epsilon, but this part, it should be controlled by guessing some other value of delta. So we say guess delta to be less than or equal to 1, then from here, we have x minus 2 less than 1, which means that x minus 2 is less than 1 but greater than negative 1. So we add 2 to all three sides. We have x is less than 3 but greater than 1. Okay, so from here on, we need to mimic this expression for this x. What do we do in this case when we don't have something similar to the previous example where we had x plus 4, where we cannot just simply add 4 to all the sides? We need to plug in 1 into this expression and 3 into this expression and see which one produces the bigger value, which would be your upper bound. So when you plug in 1, you have 1 squared plus 2 times 1 plus 4 less than x squared plus 2x plus 4, and then less than 3 squared plus 2 times 3 plus 4. This one would give us 1 plus 2 plus 4, that's going to be 7, less than x squared plus 2x plus 4, less than 9 plus 6 plus 4, that's going to be 19. So therefore, x squared plus 2x plus 4 is less than 19. So we choose this to be our upper bound. Now, x cubed minus 8 equals to x minus 2 times x squared plus 2x plus 4 is going to be less than 19 times absolute value of x minus 2 less than epsilon. So from here, we can divide everything by 19 and we get x absolute value of x minus 2 is less than epsilon over 19. And this is what we choose our delta to be. So choose delta to be minimum of 1 and epsilon over 19. Now, second step is the proof. If x minus 2 is greater than 0 but smaller than delta, then we multiply everything by 19, and we have 19 times x minus 2 less than 19 times delta. And we also probably need to write at the beginning that, to be more rigorous, given epsilon greater than 0, choose delta to be minimum of 1 and epsilon over 19. Then we continue on. If x minus 2 absolute value of that is greater than 0 but smaller than delta, then 19 times absolute value of x minus 2 less than 19 times delta. And 19 is the upper bound for x squared plus 2x plus 4, x minus 2 less than 19. And now delta is a value that is a minimum of 1 and epsilon over 19. So we will substitute epsilon over 19 here. And as you can see, they get canceled. These ones can be put into one absolute value, and we have x minus 2, x squared plus 2x plus 4 less than epsilon. And this is again the difference of cubes, and we have x cubed minus 8 here less than epsilon, and this is what we essentially needed to prove. So therefore, limit as x approaches 2 of x cubed is equal to 8 by the definition of a limit. Now, what if a function doesn't approach a finite value? Consider a function f of x equals to 1 over x squared as x goes to 0. The function grows without a bound. For infinite limits, we modify our definition. We say limit of f of x as x approaches a equals to infinity if for every m greater than 0, there exists a delta greater than 0 such that absolute value of x minus a is less than delta but greater than 0, then f of x is greater than m. So instead of keeping f of x within epsilon of L, we're saying f of x exceeds any bound m we can choose. So a quick example would be, continuing this example, we have limit as x approaches 0 of 1 over x squared would be infinity. So let me give you a sketch of this proof. So given m greater than 0, we need 1 over x squared to be greater than m when x, absolute value of x is greater than 0 and smaller than delta. So essentially we have x minus 0 here, but we don't usually write that 0. So from 1 over x squared greater than m, we get x squared is less than 1 over m, which leads us to having x is less than 1 over square root of m, the absolute value of that x. So we choose our delta to be 1 over square root of m, and we're done. So from here on, you can write your proof the same way as we did before. Now, a couple of things or final thoughts that you need to keep in mind. If you're asking yourself, if the delta must work for all epsilon, no, it should not. For each epsilon, we find a corresponding delta. As epsilon gets smaller, delta typically gets smaller too. Or if you're asking yourself, we need the smallest possible delta, which is not actually true. Any delta that works is fine. So we often choose just the convenient ones. And in our case, for the quadratic function, when we chose delta to be less than or equal to 1, that was just a convenient choice. It's not something specific. Usually just for a quadratic function that works. So this is essentially the whole idea of the epsilon delta proof.